Hey everybody, Dr. White here with the second part of the fundamental theorem of calculus. It's just a slightly different version of the same theorem. But even though it's slightly different, it has a very different look and feel and kind of a different set of applications. So I want to introduce to you a type of function that might be new to you. It's a function that takes a real number, but the way it gives you a number back is kind of elaborate. Okay, so imagine you've got some function of, say, a variable t, and here it is graphed on the t and y axis, and the function is sine of t, and so its graph is this wavy thing here, y equals sine of t. So you know that it crosses the t-axis at 0, and it goes up and then down and crosses again at 2 pi radians, and then it's negative for a while, and it crosses again at 4 pi radians. Great. Now what I'm going to do is I'm going to pick a real number x to sit somewhere on the t-axis. And I'm going to take the signed area under the sine of t curve from a starting number 0 up to the x. Okay? So it's that shaded area. Now the thing is, x is my variable here. X is the thing that I can just choose at will and make it different upper limits for this definite integral. That definite integral then becomes a function of x. Okay? So we're going to be interested in those type of functions today. Area under the curve functions, where you start at some fixed number. I'm using 0 this time, but the stopping place can vary. So, you could try out the function, like, try it out for different values of x. And, like one way is maybe you could just go to Wolfram alpha, for example. Let's see if I've got it here. Yeah. Let me find Wolfram alpha. There we go. And you could just put in, integral of sine t from t equals 0 to t equals 1. And so you've chosen your x to be 1. And it dutifully goes and gets this integral, and it's about 0.45970. And here it is trying to graph the situation for you. You can see that first hump of the sine curve taking shape there. And the signed area here is all positive area this time from the 0 to the 1. And so, you could try that out for several different values. And I've tried that out here for x is 1.1 and x is 1.2. And even x is negative 0.5. You could go integral from 0 to minus 0.5. And that works out to be 0.122, roughly. So you can do that. You could also try to find a general formula for this function. I'm going to call this function capital F of x, if you don't mind, this area under the curve function. And let's see if we can get a general formula for it. We should be able to, because we know the first version of the fundamental theorem of calculus. We can get the antiderivative of sine of t, it's minus cosine of t, and just evaluate between the 0 and the x. So we have minus cosine of x minus cosine of 0. And that works to minus cosine x plus 1. And so we could just plug different x's into that instead of having to go to Wolfram alpha each time, I'm curious, like, what's the derivative of capital F of x? What is the derivative of this area under the curve function with respect to x? Well, it's not hard to find this time. The derivative would be the derivative of minus cosine x plus 1. And the derivative of minus cosine would be minus sine, which is sine of x, plus the derivative of 0, derivative of 1, which is a 0. And so it's just sine of x, which is kind of interesting because sine of x is what you would get if you took the integrand of that definite integral and just plugged in an x instead of a t. Okay? And what I would like to point out to you is that this actually always works for any area under the curve function. Like imagine capital F of x is the integral from some starting point A, some fixed number A, up to a variable endpoint x underneath some curve, f of t. So the signed area under f of t from A to x. So here's my rough picture of what's going on. If capital F of x is set up that way, then the derivative of capital F is just, you take the integrand, put in an x where there was a t. So it's going to be that little f. So let's see if we could prove this. Why don't we let g of t be any antiderivative of little f of t? There's infinitely many of them, all separated by a constant value. Let's just pick one of them, call it g of t. So by the first fundamental theorem of calculus, the signed area from A to x of little f of t would be something you could get by taking that antiderivative g of t and evaluating from A to x. So it would be g of x minus g of a. Okay. Now, then, since we got like a nice formula for our capital F of x, got a nice formula for it now. See, that's capital Fx was that integral. We've got a formula for that integral. It looks like this. We can take the derivative of capital F. We just say, what's the derivative of capital Gx minus capital G at a? Now, the derivative of g of a is 0, because g of a is a constant. A is a constant. So I'm really only looking at the derivative of capital G of x. And since capital G was an antiderivative of little f, capital G at x must be f at x. We're done. We found that the derivative of our area under the curve function is, sure enough, just the integrand sticking an x where there used to be a t. So it's so closely related to the first part, the first fundamental theorem of calculus, that this is often called the second fundamental theorem of the calculus, or part 2 of the fundamental theorem of calculus. Another way of thinking about the second fundamental theorem of calculus is in terms of accumulation of area. So let's think about capital F of x as that signed area where the x can vary. And let's imagine ourselves thinking about its derivative using the definition of derivative. And the definition of derivative is it's the limit as some real number h goes to 0 of the function at x plus h minus the function at x over h. You know, it's that slope of the secant line that you learned in Calc 1. And you take the limit as the 2 points that make the secant line get closer and closer together. So I want to think about this, the numerator of that quantity. Now, if you think that this, if you think of it as like here's the like a t-axis, horizontal, and some y-axis vertical, and say here's the graph of like y equals f of t. And, you know, you were going to take the integral from a to x, but you're deciding like, hey, I'm going to go like a little bit further. I'm going to add like this tiny number h onto x. Then I would accumulate some extra area. And that would be this area here underneath the f curve from x to x plus h. So that would be the exact value of f of x plus h minus f of x. It would be this little shaded area here. But since this base here is really, really narrow because the h is small, then the height over the base from x to x plus h does not have much chance to vary from where it started at x. Now at x, the height is f of x. And since there's not much chance to vary, the height is basically f of x all the way through, really close to it. And so the shaded area you see here is actually really close to the area of a rectangle whose base is h and whose height is f of x. So the top of this fraction is really close to just f of x over h. And so the fraction, little secant line for the capital F, is really close to this, and the h's cancel. And so the slope of the secant line is really close to f of x, as long as h is, pretty small. And then when you take the limit as h goes to 0, that approximation has got to get better and better. The smaller you take the h here, the closer the x plus h is going to be to the x. And so the less time the height has to vary, and therefore the better this approximation is going to be. So you can see that when you get to the limit here should be exactly f of x. So that's another way of thinking about this theorem and why it is true. So we want to practice applying the theorem because of the great importance that it has in understanding areas under the curve as accumulations in a quantity. So first question for you is could you find an antiderivative for f of x is e to the minus x squared? I mean, give it a try. Could maybe e to the minus x squared be an antiderivative for e to the minus x squared? Well, if it is, its derivative has to be e to the minus x squared. So let's take its derivative here. And the derivative will be the derivative of e to the stuff is e to the same stuff times, says the chain rule, the derivative of that stuff, which is minus 2x. So no, this is not working out. The derivative is not e to the negative x squared as we need it. Now you might think, all right, we got that extra factor here. What if we try to correct for that? How could this be the antiderivative? Well, let's see. Let's take the derivative of it and see what we get. And oh wait, that's a quotient, and the derivative of a quotient, would be ho d high minus high d ho over ho ho. When you can work that around a little bit, but it's just not simplifying down to e to the negative x squared. So this is also not an antiderivative. And I tell you, you could actually struggle as much as you want and be as clever as you like. There's actually no closed form formula for an antiderivative for e to the negative x squared. But there is a way to express an antiderivative using the area under the curve function. Just let f of x be the integral from any number you like, I'm sticking a 1 here, to x of e to the minus t squared dt. And then the fundamental theorem of calculus part 2 says, hey, its antiderivative would be e to the minus x squared. So this is an important idea. Any function that you could use as the integrand for an area under the curve function would have antiderivatives. And the integral is guaranteed to exist if the function's continuous. So e to the minus t squared is a continuous function, these integrals will exist, so these antiderivatives will exist. Any continuous functions has antiderivatives, whether you can find them with a formula or not. Let's take as other examples just some area under the curve functions and see if we can get their derivatives. So how about capital F of x is the integral from 2 to x of u to the 5th du? Doesn't matter what your variable of integration is called, as long as it's not like an x that you're already using as the variable for the upper right hand, the upper endpoint. It could be any other variable at all. You're still looking at the same signed area under a function. And the derivative will be, instead of u to the 5th, x to the 5th. But let's change it up a little bit. What if you were looking at the area under u to the 5 from x to 2? And so now you're changing your lower endpoint. Then what's the derivative going to be? Well, I would, before I take the derivative, I would rewrite it. By a property of integrals, the integral from x to 2 is minus the integral from 2 to x. So I should rewrite the f this way. Then I can apply rules for derivatives plus the new fundamental theorem. Derivative of minus a function is minus the derivative of the function. And so minus x to the fifth. This should make sense to you, because if what you're varying is the lower endpoint, if you were to increase the lower endpoint by a little bit, then you're maybe chopping off some area from the beginning. And so you would expect the area to decrease. And so we see a minus here to kind of express that. The derivative of a function is the rate of change of the function. It's expressing a kind of a decrease. What if you're varying your upper endpoint, but you're varying it as a function of x, not just x itself, but some other function of x? So like the integral from 0 to x squared sine of t dt. This is actually the composition of two functions. There's kind of like an outer function, which is the area under a curve function, the area under the sine of t function from 0 to something. But the something is itself a function of x. So the composition is the area under the curve of g of x, where g of x is this function x squared. So when you want the derivative, you got to think about the chain rule. Now remember how the chain rule works. Derivative of outer composed with inner is the derivative of the outer at the inner times the derivative of the inner function. Okay, so the derivative of our capital F, it's going to be the derivative of the outer, the derivative of the area under the curve function. So that would be take the integrand and stick in your upper limit instead of the t. So that's the derivative of the outer at the inner function. But then, says the chain rule, you got to multiply by the derivative of the inner. The inner is x squared, so 2x. And so it simplifies to 2x sine of x squared if you like. Let's throw one more curveball. What if you're varying both the lower and the upper endpoints to make an area under the curve function, like this capital F of x here? So the curve, you're finding the assigned area underneath is e to the minus t, but you're varying the lower endpoint and the upper endpoint. What I would do is think about that property of integrals that says you can do a breakup. The integral from 3x to 9x plus 2 is the integral from 3x to any number you like, how about 0, plus the integral from that number 0 to 9x plus 2. Now, this I could rewrite as minus the integral from 0 to 3x. So this whole thing here is this function, but it's written in a form where I can more easily take its derivative. The derivative I can get with the sum rule. Derivative of a sum is sum of derivatives. And constant multiple rule, and the second fundamental theorem of calculus. And so I've got minus here, and then I've got e to the upper 3x times derivative of the upper, which is 3. And then I've got here e to the minus upper, so e to the minus 9x plus 2 times the derivative of the upper, which is a 9. And that could simplify a little bit if you like, but it's hardly worth it. Just want you to keep in mind what you call variables is unimportant. The variable of integration, could be a t, it could be anything you like. Here it's a w. And the variable for your upper limit doesn't have to be an x. It could be anything you like. Here's a theta. So we've got an area under the curve function of some variable theta. And the derivative would just be the integrand where you stick in the upper limit variable. Let's try one more somewhat involved exercise just to kind of challenge ourselves conceptually. What if f of x is some piecewise defined function of x, and its graph looks like this, okay? And what if we decide, hey, let's take that f and think of it as a function of t, okay? And get the area underneath it, the signed area underneath it from 0 to x. So capital A of x here is a perfectly legitimate area, signed area under the curve, function. But the area, the curve we're taking area underneath is a piecewise defined function instead of having one clean formula for all x, for all values of t. So what are we going to do? Let's see what we can learn about this capital A of x function. For example, could we find maybe like on the interval from 0 to 6, I mean, I've told you about the function from 0 to 6. So how about on the interval from 0 to 6, could we find like what's the biggest that the a will ever be? What's the smallest that the a will ever be? Find the max and the min. Well, we do know from the fundamental theorem that a prime of x has to be little f of x. Another thing I notice is that a of 0, that would be the integral from 0 to 0, f of t dt, that's going to have to be 0, because the area under a curve from 0 to 0 is really the area of just one vertical line above 0 up to the f curve, and that has 0 area. So I know that a of 0 is 0. And then I think about the graph of my function. From 0 up to apparently 1.5, the function is negative. It's below the axis. And so when you take the signed area from 0 out to some number that is less than 1.5, you are looking at negative signed area. So that means that when your x is anywhere from 0 to 1.5, the a of x is going to be, it's negative at those places, and it's getting more and more negative. It's getting more and more negative as x gets bigger. The bigger x is, the closer it gets to 1.5, the more negative area I've accumulated. And so the a of x is actually going to be decreasing on that interval from x, as x goes from 0 to 1.5. On the other hand, look at the f function from 1.5 onwards for a while. It's all the way from 1.5 to apparently 4.5, the f is positive. And so if I take the area underneath my f curve from 0 out to some number that's between 1.5 up and 4.5, well, the bigger I make my number, the more area I'll accumulate, because see, now I'm working with positive signed area over this integral. So I'm accumulating more area as I move up my x value, all the way until x gets to be 4.5. I'll accumulate more positive signed area. And so from 1.5 to 4.5, the area under the curve function is going to be increasing. So I've got that a is decreasing before 1.5 and increasing after 1.5. So a must have a local minimum right at x equals 1.5. Similar reasoning, think about what happens to the area under the curve function around 4.5. Before 4.5, you're going to be adding on positive area because the f curve is above the axis. After 4.5, you're adding on negative area in your area under the curve function. And so the function is decreasing after 4.5. And so what's happening is that right at 4.5, right at 4.5, x is going to have a local max. It's really even clearer when you think about the fact that little f is the derivative of capital A. You know, because you can just look at the graph of little f and you can say, negative before 1.5, positive after 1.5. When the derivative goes from negative to positive, your function has a local min. You can look at 4.5 and you can say, you know what? Derivative was positive before 4.5, negative afterwards. And so at 4.5, you've got to have a local max, just using that first derivative test back from Calc 1. I'm going to try to make a rough sketch of the graph of A of x. And I know a couple of things. I know that at 1.5 there's a local min, and at 4.5 there's a local max. To help my sketch out, I'll go ahead and see if I can get the values of A of x for some values of x. I've already figured out when x is 0, A of 0 has got to be 0. How about when x is 1.5? What's the signed area? Well, let's see. If I go up to this curve and I say I want to go from 0 to 1.5, look for the signed area, then I'm looking at the area of this little trapezoid doohickey down here, which is really the area of this square plus the area of this triangle I'm trying to shade in. And so the square's got area 1, and you can see the triangle's 1/2 base times height is going to be 1/2 half for the base and 1 for the height, so it's a half. And so the area of this little trapezoid here is 1.5, but that yields a negative when you do the integral because this curve is underneath the axis. And so I'm getting a negative 1.5. How about when x is, say, 4.5? Well, let's see. Area under the curve all the way up to the 4.5. So I'll get this trapezoid here that's a minus 1.5. I get another trapezoid that goes right here that's exactly the same area of 1.5. And so actually capital A at 3 would be 0. And then I get another trapezoid exactly the same size. And so I have a total of positive 1 of those trapezoids. The area will be 1.5 by this time. So when x is 4.5, the signed area underneath has clawed its way back up to 1.5. How about when x is 6? What's the net signed area? Well, you see now that you get perfectly canceling trapezoids. This one's canceling this one's getting canceled by this one. So A of 6 is a 0. So if I'm trying to make a rough sketch here for the y coordinates, I'm going to be using values of A. And for the x coordinate, I'm using these values of x. And so I can plot these points, 0, 0. I've got a 1.5 minus a half. I've got a 3, 0. And I've got a 4.5, 1.5. And I've got a 6, 0. And I know that I've got to be decreasing down to a local min and then increasing again to my local max, then decreasing again. So I can make this rough sketch. And now I'm convinced that actually this local min actually has to be a global min. The smallest I ever get for A on the entire 0 to 6 range is negative a half. The biggest I get is at this 1.5 level. That happens to me when x is 4.5. You can actually find a formula for capital A on the whole interval from 0 to 6 if you want. And I think it would be a good exercise to just see how we do that, because it actually gives us a lot of practice with fundamental theorem. Ignore this page where I decided I wanted to do it, and then I decided, no, I'm not giving myself enough space. Let me go for it here. So find a formula for capital A of x on x goes from 0 to 6. Well, the key is to keep thinking about what little f is on various little regions. I am first going to look at the x's from 0 to 1, okay, and think like, what was little f? And so I go back and I look up at little f, and it was a -1 all the way from 0 to 1, okay? That's crucial because the derivative of capital A is little f. A prime at x is little f for those x's between 0 and 1. So A prime is -1 for the x's from 0 to 1. So what could A of x be? It has to be one of the antiderivatives of -1. So it has to be a member of this family, -x plus an arbitrary constant c. And I know something as well. I know that A of 0 is 0. And so if 0 is A of 0, but on the other hand, it would be what I get by plugging in 0 for x here, then I would get that the c has to be 0 in order to capture the member of the antiderivative family that is capital A. So on 0, 1, A of x is just -x. Next, I'm going to go from 1 to 2. And the reason I'm going to go from 1 to 2 is because little f switches the rule for itself from 1 to 2. It's now this rising line that connects the point 1 minus 1 and the point 2, 1. So like if I were to use the point slope formula, knowing 2 points on a line, I could get a formula for the line. Then I'll have a little formula for little f between 1 and 2. Okay, so let's head down and see how that can help us. Well, again, A prime has got to be my little f, but if I use the if I just get the equation for the little f, knowing the 2 points on its graph, I find it has equation y equals 2x minus 3. And so I'm not showing that work here, I'm showing the results of that work. And so once again, A of x has to be one of the antiderivatives. So it's got to be x squared minus 3x plus some c, which I will determine. Now, what would A of 1, I happen to know what A of 1 is. The reason I know A of 1 is that I just can hop back up and try to find it. So what's the signed area under the F curve from 0 to 1? Well, it would be the area of this square, which is 1 times 1 is 1, but negative. So A of 1 is -1. Ta-da. So -1 is A of 1, but that's also what you get by plugging in a 1 for the x in the formula for A of x. Now we got an equation for c that we can solve for c, and we get c as 1. So between 1 and 2, the formula for A of x turns out to be x squared minus 3x plus 1. You can continue this kind of reasoning. Each step, you just choose an interval where f has one rule for itself. So between 2 and 4, the f was 1 high constantly. Between 4 and 5, the f was a decreasing line, and I used the point slope formula with 2 points I know are on the graph of f to get what f is during that time. And similarly, from 5 to 6, the f was at level -1 constantly. So on each of those intervals, I can run a similar analysis. And by the time I'm done, I have this kind of complicated but totally valid piecewise defined formula for A of x. So you can do it. And along the way, you realize how important, the fundamental theorem of calculus is in being able to isolate one desired antiderivative for a function out of a whole family. let's try one more exercise. It's number 47 in the book. There's a picture there I'd like to look at. So let me see if I can find the book. Here it is. And I need to go to this section. Alrighty. And actually, I want to go to the exercises and look for number like 47. Okay. And so it'll take a minute. I've noticed this on the computer. Maybe you've noticed it by now. It takes a minute to like fix all the math and look right. And then it pops me up to the beginning again. It's annoying. But we'll be all right. Find 47 again. Yeah, okay. So let's let a of x be the integral from 0 to x of f of t dt, where f is something whose formula they don't give you, but they give you this rough graph of f down here. And they're showing f as a function of x, even though, you know, it's written as a function of t when you do the area under the curve function. Could you find the intervals on which a is increasing and decreasing? What intervals of x is a increasing on? What intervals is it decreasing on? Well, you don't have to work too hard, because the derivative of capital A of x is little f of x by the fundamental theorem of calculus, part 2. And here we are looking at a graph of the derivative. So we can tell from as x goes from 0 to 4, the derivative is positive. See, it lies above the axis. So capital A is increasing on 0 to 4. It's also increasing on 8 to 12 because its derivative is positive there. It's decreasing from 4 to 8 because its derivative is negative there. How about part B, the values of x where a has a local min? We get that. Okay, local min, your function needs to be decreasing and then increasing. Okay, so the derivative needs to be negative and then positive. There's going to be a local min at 8 because the derivative switches from negative to positive there. How about a local max? Are there places where there's a local max? So that would be where the derivative switches from positive to negative. There's going to be a local max at 4. I guess there's also going to be a local max at 12. How about part C, the values of x where there are inflection points of a? Now, let's see here. Inflection points are where the curve switches from concave up to concave down, or from concave down to concave up. Now, concave up, that's where your curve is increasing faster and faster, or decreasing slower and slower. That's where your first derivative is increasing. And so I look, we're concave up between 0 and 2 because the derivative is increasing there. And then the derivative starts decreasing for a while. And so there was a change from concave up to concave down. Concave down is where derivative is decreasing. A change from concave up to concave down right there at x equal 2. So there's an inflection point at x is 2. There are going to be inflection points where your derivative changes from increase to decrease or vice versa. So I see another inflection point at x is 6, another inflection point for the a function at x is 10. Really neat. That's enough to work with this example, number 47. I think we're good to go for this section. You can try out, odd-numbered homework problems and try out the, the WebAssign and so on for more practice. Let me see if I can figure out where to end. See you later.